All right, today we're diving into the invisible world that honestly powers just about everything around us. We are talking about electric fields, this unseen influence that dictates the push and pull between pretty much everything. So let's start with a question that really bugged the heck out of early physicists. How can one object push another without ever touching it? You bring a charged thing near another charged thing and it moves. But how? There's nothing connecting them, just empty space. So how is that force getting from point A to point B? This was the big mystery of action at a distance.
And this diagram here shows you exactly what we're talking about. You've got this positively charged rod, and then you have this little positive test charge. The rod pushes the test charge away with a force. We'll call it F. But again, how does the little test charge even know the rod is there? What in the world is going on in the space between them?
Well, to solve this puzzle, physicists in the 19th century, especially the brilliant Michael Faraday, came up with a totally game-changing idea, the electric field. It's like the universe's messenger service, the middleman that carries the force through space.
Here's the big idea, the key insight. What if the charged rod isn't directly pushing that other particle? What if, instead, it's actually changing the very fabric of the space all around it? And then any other charge that wanders into this altered space feels a force from the field itself right at its own location.
Now, the idea of a field might sound a little abstract, but you're actually familiar with it. Think about the temperature in a room. Every single point in that room has a specific number, a temperature. That's a scalar field. It just has a magnitude. But an electric field is what we call a vector field. And that means at every single point in space, it has two things, a strength, that's the magnitude, and a specific direction.
So how do we actually measure this thing? Well, we define the electric field, which we call E, as the force, F, that a tiny positive test charge, we call it Q naught, would feel at that spot, divided by the size of the test charge itself. And this is super important because by dividing out the test charge, we're left with the property of space itself, measured in newtons per coulomb. It's totally independent of whatever we used to measure it.
And voila! Here's the solution in a picture. The rod creates this electric field, shown by that little arrow, E. The test charge just feels the field right where it is. Problem solved. Action at a distance isn't some spooky, mysterious thing. It's just a local interaction with a field that's already there.
Okay, so this field is invisible. How in the world are we supposed to visualize it? How can we map out its strength and its direction? Well, that's what we're getting into next.
So back to our hero, Michael Faraday. This guy just had this incredible, intuitive grasp of physics, and he came up with this brilliant way to see the fields that we still use today, electric field lines. He literally just imagined these lines of force filling the space around charges, giving us a visual map of the whole thing. And reading these maps is actually super easy because they follow a few simple, really powerful rules. First, wherever you are, the arrow on the line tells you which way a positive charge would get pushed. Second, look at how close the lines are. Where they're all bunched up, the field is really strong. Where they spread out, it's weaker. And finally, the lines always start on positive charges and end on negative charges. That's it. So let's see those rules in action. It's pretty straightforward. For a single positive charge, the lines just shoot straight out in all directions because, any other positive charge would be pushed straight away. And for a negative charge, the lines all point straight in, showing you the direction of attraction. Simple as that. But things get really interesting when we bring charges together. Here we've got a positive and a negative charge next to each other. This setup is called an electric dipole. And just look at how the field lines beautifully sweep from the positive charge over to the negative one. This dipole pattern is one of the most important shapes in all of physics and chemistry. You see it everywhere. Now, you might be wondering how we figure out these more complex patterns. The rule is actually way simpler than you'd think. It's called the principle of superposition. To find the total electric field at any point in space, you just figure out the field from each individual charge, and then you just add them up as vectors. That's it. Nature makes it that easy. Okay, so this is all really cool theory. But let's get to the real question. Why does any of this matter? Well, it turns out that understanding and controlling electric fields is basically the foundation of most of our modern world. Let's look at a couple of everyday examples. So, let's talk about the humble inkjet printer. You've probably used one a million times, but did you know it's actually an incredible little physics machine? Yeah, the way it works depends completely on using an electric field to steer tiny charged drops of ink with mind-boggling precision. The whole process is just wild. First, a little drop of ink is given a very specific electric charge. Then, it's fired between two plates that create a perfectly uniform electric field. This field then pushes or pulls on the charged drop, deflecting it up or down. By controlling the exact amount of charge on that drop, the printer can steer it to land on the exact right pixel on the page. It's amazing. But this idea of a field pushing on charged things isn't just for your office printer. The very same principle is at work in a device you almost certainly use every single day.
And the secret ingredient here is the water molecule. You see, because of its bent shape, the oxygen atom is kind of greedy. It pulls the electrons a little closer. This makes the oxygen side of the molecule slightly negative, and it leaves the two hydrogen atoms slightly positive. And what does that make a water molecule? A natural teeny tiny electric dipole.
So what happens when you put your food, which is full of water, into a microwave? Well, the oven creates an electric field that flips direction back and forth billions of times every second. This oscillating field grabs on to all those little water dipoles and tries to line them up. But since the field keeps flipping, the water molecules are forced to twist and turn and wiggle back and forth like crazy. And all of that frantic molecular wiggling and dancing around? Well, that's what heat is. All that motion transfers energy directly into your food, cooking it from the inside out. It's an absolutely incredible application of physics. Seriously, if water wasn't a dipole, your microwave would just be a metal box with a light in it. So we've gone from a strange puzzle about forces to a way to draw invisible maps, all the way to the technologies sitting in our homes. But the story here is even deeper, even more fundamental. This is probably the most profound thing to take away from all this. The electric field is not just a clever math trick we invented to make calculations easier. No, it is a real, physical thing that fills space. It's there, whether or not we ever put a charge in it to feel its effects. When you get right down to it, the electric field is a fundamental part of our reality. It's the carrier for the electromagnetic force, one of the four bedrock forces of the entire universe. It's what holds electrons to atoms. It's what binds atoms into molecules. It's what powers our world. It is, quite literally, everywhere. And that kind of leaves us with one last big thought. We just explored one invisible field that has this immense, world-shaping power. So it really makes you wonder, right? What other fundamental, unseen forces are out there, quietly shaping the universe all around us?